been talking about the dot product and some applications that we can use vectors, the projection, the vector projection, and some applications. So we did this, you can't see anything. Let me turn that on. We were working on this example problem last time, where we had this question about how much force is being applied at an angle. And we made an observation at that point that, hey, it seems like the dot product of those two vectors turned out to be the magnitude of the projection. And if that's always the case, that's a tremendous time saver, because you don't have to really do the vector projection. You don't have to do the magnitude. You just do a dot product of two vectors. And that's a pretty easy calculation to do. So let's talk about when that shortcut will work and when it won't. So if we have two vectors, u and v, if v is a unit vector, then the magnitude of the projection of u onto v is equal to, well, we should say the absolute value of the dot product of u and v. Which is pretty righteous, right? All we need is that v is a unit vector, that the vector we're projecting onto. So if we go back to that original problem, we were projecting onto this hill vector, and we're given any length in the story problem for the hill. We're just told the hill has some angle of incline. Well, that to me tells me that I can pick the length of the hill to be anything I want. Namely, I can pick it to be a unit vector. And we're good to go. We can use this shortcut. Let's prove this, though, just so that you're certain, or we're certain, that this works. Hey, Prater. So we'll just start off by declaring we have two vectors u and v, where one of them's a unit vector. I know the formula for the projection of u onto v is, you remember? It's the dot product of u and v over the magnitude of v squared times vector v. And we know the magnitude of v is just 1. So when I do that scalar multiplication, I get u1 times v1 squared. Well, let's write it this way. Probably going to be more convenient writing it this way. So far, so good. All right. So then if I want the magnitude of that projection, I'm going to do the square root of the first component squared plus the second component squared. Is okay there. So I know when I have the exponent of a product, I can rewrite that as, or apply the exponent to each factor of the product. Is okay there. And then I notice, hey, look at this. Like that's a common factor to everything underneath the radical. So I can like factor that piece out. Everybody's okay with that? And if I have the square root of a product, I can think about those as two separate square roots, still multiplied together. So if I look at that first one, the squared cancels the square root, but I know that when I square something, it has to be positive, and when I take the square root of a positive, it has to give me a positive back, so that's like the absolute value. And this right here is just the formula for the magnitude of V. And if I recognize this in here, that's the dot product of U and V. And I know that the magnitude of V is just 1. So I have that as long as V is a unit vector, that the magnitude of the projection of U onto V is the same as the absolute value of the dot product of U and V. That's our proof. Would I ever ask you to do that again? No. But it's like this is the honors class. When I show you something, we're going to prove it more often than not because that's what we do, right? You don't get to, you can trust Mr. Kulik, but you shouldn't trust him too much. You should make him prove it. If I say something like that, you should want me to prove it. Okay. Let's do another example that's a little bit different than the previous one. So here it says a crate is being pulled up a ramp at an angle of 40 degrees with a force of 100 pounds. The ramp measures 10 feet horizontally and 2 feet vertically, assuming that the crate is of negligible weight. What is the amount of force directed up the ramp? Okay, so the key thing here is in this problem, the ramp has a length. So I cannot use that shortcut that I just used. because I no longer am dealing with a unit vector. So if I want to write a component form for a vector r, what should I write its component form as? 10, 2. Yeah. 10 feet horizontally, 2 feet vertically. That should be the component form 10, 2. Ah, okay. Whoop-de-de-doo. That's tough. And then I have a force vector. Now that force vector, I'm not given a component form for it, right? I'm given an angle and a magnitude. No, let's just write it that way. But that's fine. I can just resolve that into a component form. I have a formula to do that. So far, so good. So what I want then is the projection of F onto R. That's what we're going to be looking for. I'm going to do the projection first and then do the magnitude after. It just turns out to like be neater, I think, to do it that way. So the formula for the projection of F onto R is the dot product of R and F divided by the magnitude of F squared times, the magnitude of R squared times vector R. So if I do that, I'm going to have 1,000 cosine 40 plus 200 sine 40 divided by the magnitude of that's going to be the square root of 104, the square root of 10 squared plus 2 squared. I'm just going to write a square root 104. Since none of this stuff is going to be permanent answer, I don't care that that radical could reduce. I don't care that that radical's in the denominator. It's not going to be part of a final answer anywhere, so I'm just going to leave it the way it is and not make more work for myself. And then I have that all times vector R. So if I do that, I'm going to have, if I do that scalar multiplication, I multiply 10 to everything in the x component. Or I should say I multiply that thing by 10. And then multiply 2 to that stuff. Oops. Okay, there. And now I just need to do the projection, or the magnitude of that. And that I'm just going to do in the calculator rather than writing this all down because it's already getting pretty woofy to me. So I'm going to do this as like 3 lines. So I'm going to do this fraction, then I'm going to do this fraction, and I'm going to do the square root of each of those answers squared. Just so everybody's clear as to like how I'm going to type this in. I could type it in all in one line if I wanted to, but just feels like it's going to get too messy for me. Ooh. So the magnitude of r is square root 104, but that's squared. So it should just be regular 104s. Oof. Caught it. Shame on you guys for not noticing. I'm just joking. I mean, but not really. All right, so I got that in there. We'll do the same thing for the other one. So 2,000 cosine 40 plus 400 sine 40 all over 104. So that's that. And then the magnitude is going to be this thing squared plus this thing squared. So I should get about 8772. I guess I should put an approximation symbol on that. And since the unit for force in the problem was given as pounds, I know the unit that I'm going to get out of this should be in pounds. Is that okay? So again, this problem, or these kinds of problems, are kind of all the same. What's hard about it is you need to remember the dot product formula, the projection formula, recognize the scalar multiplication that's happening. You need the magnitude formula. It's like all the vector operation formulas kind of all coming in together. As an aside, if this problem was a little bit different, I think this happens in the homework. We have the assuming the crate is of negligible weight. What if the crate did have some weight to it? Then you'd have like this force, and you'd have a second force from the crate, weight of the crate, say like it's 100 pounds or something. And then you would want to add those two vectors together, and then you're going to project that vector sum onto the ramp. So whether you had one vector, two vectors, three vectors, four vectors, whatever many of vectors that you're projecting, just add them together and then do the projection on the sum. So that's the only kind of change that might happen, but essentially all these problems are kind of the same. Now, ideally, you're hoping for ones like this first one, where you're not given any information on the length of the ramp or the length of the hill or whatever you're projecting onto, so you can just shortcut straight to the dot product and just be done with it. Because Lord Almighty, that's a big simplification. But if you are given a length in there, you have to go through the whole rigmarole. So looking at this, so this one, you can use the shortcut on, right? Because there's no length given to the hill. This one, again, you can use the shortcut on. There's no length given to the hill. This one, again, you can use the shortcut on. No length given to the hill. This one, we are given a length for the ramp. So you have to do that one the real way. This one, you're given both a weight for the crate and a force. So you're going to have to add those two forces together. But the ramp has no length to it, so you can use the shortcut afterwards, which is lovely. And then the last one, same deal. Again, you have two forces, but the ramp has no length to it, so you can use the shortcut there as well. So Do you guys feel okay with these kind of story problems? They're a little tricky, but you do the problem set problems, and it should get, by the end of it, you should feel pretty good. They're not so bad, and I feel like we've walked through it pretty carefully here with these couple of examples and talked about the different cases, and going through this and kind of just identifying what's going on in the problem quickly is probably helpful, so that you're not spending like 10 minutes reading the problem and making a mess out of it. Okay. So this would be like the last topic that would appear on the homework quiz, would be up to this point. I know we had it scheduled for today. We're not going to do it today because I didn't finish this stuff. So it'll be next time. But this would be the last topic. I would say would be fair game for the homework quiz. So I would want to definitely be through whatever problem, like 30 or something, 50, by that point. Not that it's all that stuff is due necessarily by next class, but all right. Everybody feels so far so good? I'm going to continue on into section 8.4 now. These topics would not be on the homework quiz, but still are like important topics that, well, you need to be able to do for the test or whatever. So 8.4 is about 2D vectors in space, which sounds like an action movie title or something. No? Fine. I'm trying to make jokes. So we're going to start by defining another notation that we can use to represent a vector. So the text that we use calls this IB component form. In Mr. Kulik's math education, I'd call this a column vector. So just the x component is top and the y component is on bottom. It's really the same thing. It's just written vertically instead of horizontally. Whatever. Okay. So what we're going to talk about here first is kind of translating or creating a, what do we want to say? Let's call this, So what we're going to start by doing is creating a vector equation for a line. So just like in your Algebra 1 class, what sort of information did you need to be able to write the equation for a line? Slope and? Okay, well, let's just be more general and just say a point, right? Would be enough information to write the equation for a line. What else could you use? Right? Just like 2 points is enough, correct? It's going to be very much the same idea here if we're using vectors. Either of these two would be enough to write the vector equation for a line. So let's take a line that we already have. So let's say, for example, we just have something like y equals 1/2 plus x. So here is our graph of our line, right? So we have a line. How many points lie on a line? Infinitely many, right? You need 2 points to draw the line, but the line contains infinitely many. Let's just say we pick one of them. Could be any point. I'm going to place it here at 2, 2 for our purposes. But I'm just going to call that like that point P naught. And it could be any point. It doesn't have to be 2, 2. It's just going to make the calculation later convenient that I picked it like a point with round numbers to it. So if I wanted to draw a vector to represent, it's the projector again. It's that terrible squeaking. To represent this, I would draw like a vector starting at that point, and it could go in that direction or it could go in that direction, right? Either of those would be fair game for a vector to represent this line. You guys agree with that? Okay. So the slope for this equation is 1/2, right? And what does slope mean? Okay. What is a slope of, like, that's true? How about in terms of like x and y? Okay, so it's like change in y over change in x. Everybody agree with that? So that means that our slope is going to be for like every 1 unit we move to the right, we have to move 2 units up. I have that reversed, right? 2 units, 1 unit, sorry. Now, if I want to express that as a vector, what would we say the vector is that expresses that idea? So it'd be the vector 2, 1, or really we're going to write it as that column vector notation. Number one place, students make a mistake when they take their slope to their line. They put the x's and y's in the wrong spot because they just turn the fraction into the column vector, not thinking that slope is change in y over change in x. So you need to flip the numbers in your slope when you translate that to a vector. So we could say then, like, our vector equation should be, okay, we start at point P, and then we do vector V, right? What's wrong with this? This is a point. This is a vector. Can I add a point to a vector? No. Another thing wrong with it, this is a variable representing a number. This quantity should be a vector That's not appropriate either. So we need some cleanup here a little bit. We need this to be a vector. Well, how do I do that? I literally just like take the x coordinate from the point, make it the x component for my vector, and take the y coordinate from my point to make it the y component for my vector. Easy enough. So if I do that, I can say, okay, y is the point P plus the vector, or the vector P naught plus the vector V. But remember what's going on here. P is just a fixed value. V is just a fixed value. So we're just getting another vector 4, 3, right? Is that representing like, would that represent any vector that we could draw here? No, right? Like what if we wanted this vector here? Well, that's certainly not vector 4, 3, but it's equivalent to the line we've drawn. Everybody agree? So we need to put like some kind of parameter in here so that we can get a vector that starts at P, that has the slope of 2, 1, but can be any length. So what do we do there? Well, I'm just going to add a parameter here to my vector V. I'm going to call that parameter T. So this is now like a function in terms of T. Notice that T is not a vector, it's a scalar. So if, say, T equals 2, we'd have the vector 6, 4, which again, we're going to notice is parallel to this one, right? In fact, they are, if I plotted both of those, they're going to be on the same line, right? One is just going to overlap the other. Notice what's going to happen if T is negative. That's also a vector that lies on that line, but it's going to be pointing the opposite direction. That's how we can get the vectors going that way. Everybody okay with that? Now, the last thing is more of a notational thing than anything else, right? P naught, a vector, plus a scalar times a vector needs to be another vector. We've written it as a variable still. So we need to just turn this into a vector. So the final form the way we write this is oops. So that's our vector equation for a line, where r naught is our point vector and v is our slope vector. Okay, let's do a couple of examples here playing with this. Okay, say I want to convert from this slope-intercept equation into a vector equation for a line. So I know I'm going to be using this formula. So my point vector can be any point that lies on the line y equals 3x plus 5. What would be the easiest point to use? 0, 5, the y-intercept, right? V is the slope vector. What's the slope vector here? Or what's the slope for this line? 3, so my slope vector should be 1, 3. Are these the only possible values I could pick? No, right? I could pick any point on the line, like I could have done 1, 8 or negative 1, 2 or whatever. Even the slope vector, I could have written it as negative 1, negative 3 or 2, 6. Anything that's equivalent slope-wise. So there's like infinitely many answers to this. That's why it says a possible. Now, I don't know why you'd write it any other way than this, but you could. It's not wrong. Now, that was pretty easy, right? Bless you. No problem. What if we wanted to go the other way? What if we wanted to take our vector line equation and write it into, say, slope-intercept form? What are we going to do that? Well, the slope would be 3 over 2, sure. What else do we need to write the equation for a line? Any point would be fine. The y-intercept would be nice, but not easy to generate the y-intercept out of a vector line equation. But any point would be okay. So we're just going to go ahead and pick a value for t, maybe 0, in which case we get the 0.31. Sorry, 3, negative 1. So then I can write my equation for a line. You could do this with slope-intercept form, or you could do the point and slope form equation. Either is okay. I like the point and slope form equation because I don't have to do any like solve for b and then rewrite b afterwards. So if I distribute things, simplify things down, I have 3 over 2 minus 9 over 3 over 2x minus 9 over 2. And if I just subtract 1 from both sides, that'll be minus 11 over 2. Everybody feels okay doing that, going back and forth between these two forms. Pretty easy, right? We're basically doing like just rewriting stuff or doing like algebra 1, write the equation for a line type of problems. Alternatively, worth mentioning, you could also, if you weren't confident about the slope, you could just generate 2 points from the line and find the equation for a line that way. You don't need to do it that way. This is fine, but you could do it that way also. Giselle? I just picked one. Sure. No, I just was showing you like how you plug stuff in. But yeah, you could have said the same thing just by looking at it. You know, that this is a point vector. Sure. No problem. Okay. What if we want the intersection of two vector line equations? So reminder, what are the 3 things that can happen? If you're talking about if you have 2 lines and you're concerned about their intersection, what are the 3 things that can happen? Well, the simplest is they can intersect once, right? What else could happen though? They could be parallel, so intersect 0 times. And what's the third thing that can happen? They can intersect infinitely many times. That means they're coinciding or they're just the same line, right? Every point on one line intersects with every point on the other line. Do you guys remember this from, I think when you solve systems in Algebra 2, you spend a bit of time talking about these outcomes. So the same thing can happen for our vector line equations. So let's look at an example there. All right. So the obvious route would be to do what? Braden? Sure. Okay. But if we want to find that, and then if we want to find that point of intersection, what would the obvious thing to do? You could convert them both to slope-intercept forms and then solve the system algebraically, right? That's the obvious route. That's not what we're going to do. And while that may be technically a little bit simpler in the case of a 2-dimensional, if this was 3-dimensional, 4-dimensional, or 5-dimensional, you've seen that that's like, can be really kind of a pain. So we're going to look at this in a different fashion, take advantage of some of our vector mechanics that's going to scale very nicely to bigger systems. Everybody's okay with that? Okay. So if, you know, R1 and R2 intersect, there would be some point xy that lies on both lines, right? Now, in vector speak, it would mean like there exists some vector xy such that xy is a vector output from R1 and xy is a vector output from R2. So if I say that, I can say xy should equal the vector 2, 4 plus the vector 1, 3 times s. That's just R1. And likewise, I can say xy should equal the vector negative 1, 5 plus the vector 3, 5 times t. That's just my R2. If I go ahead and I add and do the scalar multiplication for those vectors, I can say then xy has to equal the vector 2 plus 1s, 4 plus 3s, and similarly, it has to equal negative 1 plus 3t and 5 plus 5t. Everybody's okay there? So if these two are equal, the x coordinates need to be equal and the y coordinates need to be equal. So what that has done is created for me a system of two equations. Everybody's okay with that? What was the easiest way we had to solve a system of two equations back in Algebra 2? Or the fastest? The least sweat? I would say I would say if you're doing it by pen and paper, yes, that was the best one. But what else did you have? And what else did you have other than substitution and elimination? How did you do this on a calculator? You turned it into a matrix and you used the row reduced echelon form operation on the matrix. And it spat out our system for us, right? So we'll review how to do that right now, okay? So first thing I'm going to need to do is rearrange my matrix, or rearrange my system so that I can turn it into a matrix. That means I have to get the stuff with the variables on one side of the equal sign and the stuff without the variables on the other. So I'm going to subtract 3t over and then subtract 2 over. Similarly, I'm going to subtract 5t over and then subtract 4 over. The system I've written here now can be translated into a matrix. You have to be careful when you're doing this because the variables all have to line up. and then you have to have the equal sign, and then you have to have the constants. Has to be in that order. So the variables have to line up vertically. The equal sign has to line up vertically. The constant has to line up vertically. So to turn this into a matrix now, what I'm going to do is I'm going to press second, and then the matrix button, which is, you notice in blue above the x to the negative 1 button is the word matrix. That opens up the matrix menu. The matrix menu has 3 tabs. It has the names tab, the math tab, and the edit tab. To enter a matrix, we're going to use the edit tab. And we're going to select a matrix to use. All the first 4 of mine have already all been used before. That doesn't matter. I'm just going to like change the size of it or whatever and just type over what was in there. So I'm just going to do mine in matrix A. So this 3x4 is the dimension of the matrix. You guys remember that term? Which dimension is first, rows or columns? Rows are first, columns are second. If I look at the system I've written, how many rows do I have? 2. How many columns do I have? 3. I don't need a column for the equal sign, even though I circled it. And what do I type in now? I just type in the coefficients from my system. So the first number I'll type in is 1. That's the coefficient on S. And then -3, that's the coefficient on T. And then -3, that's my constant. And then I'll type in the next row, I'll do 3, -5, and then 1. Notice when I wrote S, I wrote 1S just as a reminder to myself not to put a 0 there. Very common mistake I see students make is if they don't see a coefficient, they put a 0. When if there's no coefficient, we should understand that there's a 1 there that we just usually don't write. Okay? Once I have all my numbers inputted, that sounds wrong vocabulary or like grammar-wise, inputted. Input? I don't know. Anyways, we're going to exit out of here, so we'll press second and then the mode button right next to it. We'll call back up that matrix menu. And this time we're going to move to the Math tab. From the Math tab, we're going to scroll down almost to the bottom, and we're going to look for the RREF command. That's row reduced echelon form. We'll select that. And then we're going to do that RREF on that matrix A that we just made. So go back into the matrix menu for a third time. From the names column, I'm going to select matrix A, which was the one I just input my numbers in. Close my parenthesis and press enter. You go back to the matrix menu, you go over to the Math tab, and then it's like almost at the bottom. You just keep scrolling down. It's like Command B or something. You found it? No problem. Okay, so how do I interpret this? I have 1S plus 0t is equal to 4.5. So I have then that S is equal to 4.5. I then have 0s plus 1t is equal to 2.5, or t is equal to 2.5. So my solution is the point 4.5 comma 2.5, right? Wrong. What I found here is if I go back and I plug in the S value of 4.5 or the T value of 2.5 into my vector line equations, I should get the same vector output, which would be the point of intersection. So I have one final step. So I'm going to do R1. Where's my, I need it on, of S. So when I do that, I get 4.5 plus 2 is 6.5. 4.5 times 3 is 13.5 plus 4 is 17.5. Or if I had tried to do R2 of 2.5, that was negative 1.5 plus 3.5 and then multiplied by 2.5. So 3 times 2.5 is 7.5 plus negative 1 is 6.5. That's a good sign. 5 times 2.5 is 12.5 plus 5 more is 17.5. So this guy is my solution. Everybody's okay with that? Now, Braden made an excellent point early on, is that the first thing we should really do is do some checks, right? We should check to see if R1 is parallel to R2. So how would I do that? I would see if K times the slope vector for R1, if I can find a constant so that that's always true, then I know they're parallel. If the answer's, oh, that doesn't tell me that, parallel. So that means if it's yes, they're either parallel or coinciding, right? No, that means there's just one intersection. Everybody's okay with that? Now, how am I going to tell the difference between parallel and coinciding? If we do the intersection and there's a solution, what's that going to tell me? Or actually, let's do that. Let's do this. It's even easier. I take R naught from equation 1 and I plug it into the equation for line 2, and if that point R1 lies on R2, then they have to be coinciding, because if you have the same slope and one point from one line is on the other line, have to be identical lines. That's even easier, right? So the answer here, if it's yes, we are coinciding. And if the answer here is no, then we are parallel. So let's just want to cook up an easy example to just kind of run through what that looks like numerically. Right? So I don't have a pre-made example, so I'm just going to make something up that's like you're going to look at it and you're going to go, okay, like I can look at this and tell that this isn't, you know, what this is. But that's okay. Okay, so you look at these and you can probably see right away that these are coinciding, right? Super obvious. We're going to just run through the process, though. That's the point of this, is just to see what it looks like numerically. So first thing we're going to do is check the slopes. So I want to see, is 1, 1 times k, is that a scalar multiple of -1, -1? So this just becomes like k times k, or kk. And we're just seeing, so let's write it this way. So if I solve the first one, so that tells me k is equal to -1. If I solve the second, k equals -1. So I know that these are either parallel or coinciding. They have the same slope. If, for example, this was like 1, 2, then you'd have something like that. Now they can't be parallel because you need a different k to make them the same, right? Now that's not what we had, so I'm going to just back that out of there. So the next thing we're going to check is we're going to just take the point from R1 and plug it in to R2 and see if we can solve that for a single t. So I have 1, 0 is equal to 2 minus t, and then 1 minus t. So that just becomes the system. 1 equals 2 minus t. So t is equal to 3. Oops. Or 1, dum-dum. And then 0 is equal to 1 minus t. So t is equal to 1. Because they're the same t. So yes, that point lies, you know, like, what is it, like R01 lies on R2. So we're coinciding. Since we have the same slope and one point from R1 lies on R2, all of the points from R1 have to lie in R2 because the slopes are the same. You're just going to be moving left and right, or up and down, left and right the same amount to get to the next point. Does that feel okay? Okay. And this is a good scaffolding because we're going to build on top of this in 3 dimensions where there's a fourth thing that can happen. But we're going to stop here for today. This feels like that feels like a good place. That's a good stopping point. So let's look at here. Where could we go up to now? 2D, 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 all the way to 76. Can I just write like up to 76? You guys are okay with me just writing that? I mean, you're probably not okay with that many problems, but like, you understand what I mean. Understand what I mean. So let's take a pause here and talk about what's due, right? So Sunday, I think I have 23 for 50 written down, but I don't like that because it wouldn't give you a chance to ask about this projection stuff. So let's just make that to 40 for Sunday. I'll update my Notre Dame here later today. And then next Sunday, what is that, the 29th or something? And then next Sunday would be like the 5th. You'll have 50 to 76 at least, and then probably we'll add some onto there. Does that feel okay? Again, there's whatever 140 something problems in this chapter. Don't get behind, right? Like, try to stay on top of things. It snowballs pretty quickly. If you're waiting to Sunday to do things, you're going to hate yourself come Sunday. So please, please, please kind of stay on top of things. Reminder, next class you should expect a homework quiz. The homework quiz will go up through 8.3. So you should be familiar with like the vector operations, like changing forms of vectors, doing those like simple stuff, and then like the vector application story problems is kind of where we stopped. So you should be good up to there. And I'm going to stop talking now because I think I talked about everything I needed to. You guys cool?